Hello again, this is the last section of chapter 7. By improper integrals, we're referring to either type 1 or type 2. An improper integral of type 1 will have one of the limits of integration infinity or negative infinity a from f of x dx, or a to infinity from f of x dx, or both infinities, negative infinity to infinity from f of x dx. And you will see what happens. We're going to use limits to evaluate these limits. If the limit exists, then we say the improper integral converges. If the limit does not exist in any of these situations, then we say diverges. So the integral will be calculated using limits. If the limits exist, we will say about these integrals, or any type we have of type 1, any of these three, we say the integral converges. If the limit does not exist, then we will say that the integral diverges. What about type 2? In type 2, the function is undefined, either at one of the upper limit or lower limit, or somewhere in between. So we can have the integral from a to b from f of x dx, but f of x is not defined at a. F of x undefined at x equals a. The other option will be the integral from a to b from f of x dx, but the function f of x is undefined at x equals b. And there is a third option when the function is undefined somewhere, not at a or b, but somewhere in between. So the integral from a to b from f of x dx, but f of x is undefined at x equals c, and c is a number between a and b. The answer will be determined the same way, using limits. Again, for the same procedure, if the limit exists, then we will say that the integral is convergent. If the limit does not exist, we will say the integral does not converge. Okay, I want to just establish two things from the very beginning. And we can prove this. They're proved in your book. So the integral from 1 over x to p, of course, from 1 to infinity, dx, is convergent for p only strictly greater than 1, and is divergent for p less than or equal to 1. Okay, so this is a very important result. Very important. Okay, so let's look at examples from each. Let's see how we address this. Okay, I'm on my page 2, and I'd like to pick some problems, like, for example, 9 on page 549. So the integral is from -2 to infinity, from 1 over x plus 4 dx. When we look at the two types, we know that this function is not defined at -4, but -4 is not in the interval. So that's not the issue. The issue is right here. One of the limits, so it's type 1. One of the limits, either lower or upper, is a infinity. So in that case, we will replace this with a limit as t approaches infinity from -2 to t from 1 over x plus 4 dx. We already know that this is limit t approaches infinity from natural log of the absolute value of x plus 4 from -2 to t. We plug in t, so this is limit. Do not drop the limit operator, please. Natural log of t plus 4 in absolute value, and minus, when I plug in -2 plus 4 is 2, so minus natural log 2. When t approaches infinity, this quantity will approach infinity. Therefore, the answer is infinity. Therefore, we conclude from here that the integral from -2 to infinity from 1 over x plus 4 dx diverges. Okay, moving on. Let's look at number 19 on 550. The integral from -infinity to infinity from x e to -x squared dx. This function exists for any x, but the problem is that both limits of integration are infinities. So in that case, we will use limit as x approaches -infinity. Not yet. I want to write one more intermediate step, so maybe I can fit it in here. So the integral from -infinity to 0, e to -x squared dx, plus the integral from 0 to infinity from x e to -x squared dx. And then we're going to put in the limit. So I'm going to move on to the next page, not before I take care of this. I have to change x into t anyway, so good, it's gone. Good. Hey, this is my page 3. Yes, so equals. The first one will be the limit as t approaches -infinity from t to 0 x e to -x squared dx, and then plus limit as t approaches infinity from 0 to t x e to -x squared dx. And let's see how we address this. Good. So in both situations, I will denote -x squared by u, du equals -2x dx. And you know how I like to do it. If it's just a simple number, I don't want to spend too much time on that. -2 and -1/2. Multiply by -2 and divide by -2. There is no change whatsoever in doing that. Okay, so we'll continue. I can even take -1/2 outside of the limit. The limit as t approaches -infinity. I don't want any confusion. We're not there yet with the integral. We still have the limit. Good. From the integral from what we have here, let me remove this. Okay, so what I have here is e to u du. E to u du. But careful, when x is t, the lower limit is -t squared. When x is 0, the upper limit is 0. Plus limit as t approaches infinity from I'm rushing and I shouldn't. Okay, limit as t approaches infinity, again from e to u du. Now careful, 0 here and -t squared up there. Good. Okay, So this is still plus. There is no change there. Good. So my next step, negative 1/2. The integral from e to u, so this is limit as t approaches negative infinity. So it's e to u from negative t squared to 0. And minus 1/2 limit as t approaches infinity from e to u from 0 to negative t squared. Good. Plug it in. Negative 1/2 when, of course, the limit still. When we plug in 0, we get 1, minus when we plug in negative t squared, minus 1/2 limit as t approaches infinity, e to negative t squared and minus 1. Now, regardless of where t is going to negative infinity or infinity, this quantity is still negative infinity. So this will also always approach 0. So let's see what is left. If these are 0, so we have negative 1/2 limit of 1, which is negative 1/2. Negative 1/2 limit of negative 1, which is negative 1 times negative 1/2, so it's positive 1/2. The answer is 0. Therefore, we conclude that this interval converges. So I'm going to write it on the next page. That's page 4. So the conclusion here is that the integral from negative infinity to infinity x e to negative x squared dx converges because the limit exists. Okay, moving on to other examples. Let's say 37. Also on 550, we have the integral from negative 2 to 14 from dx over the 4th root of x plus 2. So we know that x plus 2 has to be strictly greater than 0 because this quantity has index 4, radical with index 4, even index, but also cannot be 0 because this quantity is in a denominator. So x has to be strictly greater than negative 2. So the problem is here. Good. So then we have limit as t approaches negative 2 from above with numbers higher than negative 2. And then the integral from t to 14 dx and the 4th root of x plus 2. I will use a substitution as x plus 2 being u, du equals dx. So then this is limit as t approaches negative 2 from the right. And here we have du over the 4th root of u. So I'm going to write u to negative 1/4 du. Careful. We have to replace the limits of integration with the appropriate limits. So when x is t, then we have t plus 2. When x is 14, 14 plus 2 is 16. Good. Moving on. So then we have limit as t approaches negative 2 from the right, from u to negative 1/4 plus 1, which is 3/4, divided by 3/4, from t plus 2 to 16. Okay, so now I'm going to flip this and put it in front, 4/3. And then we have limit as t approaches negative 2 from the right. I plug in 16. The 4th of 16 is 2. 2 to the 3rd is 8. Minus the 4th root of t plus 2 to the 3rd. So let's see where this is going. So negative 2 from the right is like negative 1.9. This is correct. It's allowed. So this approaches 0. So then the limit is 8. So 32 divided by 3, because the limit exists, we will say that the integral from -2 to 14 from dx over the fourth root of x plus 2 converges. This is how we address so far these examples of improper integrals. Okay, so let's look at one more, 45. On the same page, 550. I'm going to change the color here. So we have the integral from 0 to 1 from r natural log r dr. Okay, so let's see how we address this. What is the problem here? This exists everywhere, but this requires strictly greater than 0. It's natural log. So there is a problem here. So we will have to replace this limit as t approaches 0 from the right with numbers larger than 0, from t to 1 r natural log r dr. This is typical for integration by parts. So this is limit t approaches 0 from the right, from t to 1. I'll change this into r squared over 2 prime natural log r dr. dr. Okay, so then we have limit as t approaches 0 from the right, from r squared over 2 natural log r from 0, no, from t to 1 minus 1/2 the integral from r squared times 1 over r dr from t to 1. I don't want to forget about this because I will forget. Okay, from t to 1. Good. Okay, then so limit as t approaches 0 from the right. When I plug in 1, this is 0 because of natural log 1. When I plug in t, don't forget minus t squared over 2 natural log t. Here I simplify, minus 1/2, that it's r squared over 2 from t to 1. So this is limit t approaches 0 from the right of a -1/2, and this approaches infinity and this approaches 0, so I'm going to change this function into 1 natural log t over 1 over t squared, because now this approaches infinity and this whole thing approaches infinity, and I will be using L'Hopital's rule from chapter 4. Okay, so a minus 1/4 when I plug in 1 is 1. When I plug in t, plus t squared over 4. This quantity approaches 0 because t approaches 0. So we have -1/4. Oh, which page am I on? This is 5, and this is 6. Good. Okay, so limit as t approaches 0 from the right with -1/2. I differentiate the top and I get 1 over t. I differentiate the denominator. Remember, let me write it here on the side. T to -2 prime is -2 over t to the third. So -2 over t to the third. And minus 1/4, because this is 0. Okay, so as I said, I was going to put it in front. And when we simplify, so this is positive, we can put -1/2 in front. Limit as t approaches 0 from the right. So I have 1 over t times t to the third over -2. When I simplify, I get t squared. But all this piece will approach 0. How come? Because I have t squared over -2 when t approaches 0. So this is 0. 0 times -1/2 is 0. So the final answer is -1/4. The limit exists. So therefore we conclude that the integral from 0 to 1 from R, natural log R, dr converges. I hope this helps. Thank you.